Hello everyone, do you hear me? Thank you. So we're ready to continue our exploration of BGP. Before that, a few words about the exam. There is a written exam for this course, but given the situation, we were asked to choose a form of examination that does not require your presence on campus. So what we will do for this course is a take-home exam that you will be able to do from home. Of course, we will ask you to do it in conditions that avoid cheating. And we are also working on making a form of exam that makes cheating as difficult as possible. We will give you more information in the coming weeks. But the first thing that is sure for today is that you will not need to come to campus for this exam. Well, if you have any questions, post them during the break on the news group or on the chat of this session. Right now, we continue with BGP, and we have seen two examples on how BGP routers are able to disseminate the information. Let me jump into a question. Here, we have seen an example that was a bit like this one here. We had two domains, two autonomous systems. And in the first example, we had some rules by which routers like R21 and R22 would advertise their routes to ISP1. And in the second example, the rules were a bit different. And as a result, we saw that the best routes chosen by R11, for example, and R12 were different. So now let's look at it from a more macroscopic viewpoint and say, I have two ISPs that are connected in multiple points, and I have traffic that goes from one customer of the first ISP to another customer of the other ISP, and they are located as shown on the figure. Which way do you think the traffic will go? I'm proposing several answers. I close the poll in a few seconds. And the majority says C, which is indeed the correct answer. We have seen two examples. In the first example, routers in ISP2 were advertising all the network prefixes of ISP2, and by default, if nothing else is changed, the result that routers like R11 and R12 would forward traffic to they would prefer the routes run by each BGPs. Therefore, the next hop will be the one that is their eBGP peer. In such a case, this would be the traffic, the green case would occur. But we had seen another case where the routes were advertised only locally. So in that case, only R21 would advertise a route to R11, R22 would not. So in such a case, eBGP would be preferred instead ISP1, and the route would go via the long distance. So the take-home message is, it depends on the configuration of the decision process. The case that is very frequent is the first case. And in such a case, we see that we have what is called hot potato routing. Hot potato means we get rid of the traffic like a hot potato as quickly as possible. So this is what would happen in this case. Observe that if this is the rule and if things are symmetric, if ISP1 and ISP2 behave similarly with respect to each other, traffic from customer 2 to customer 1, so traffic in the reverse direction, will follow a different path by the same rule here. So as a side effect, we find first observation is that because of BGP, you can expect that there will be cases, and in fact this is fairly frequent, where routing is asymmetric, where routing in one direction is not the same as in the reverse direction. So many cases like this occur. Operators that offer a good service often prefer the opposite. They use what is called cold potato routing. This is if ISP is a provider like, for example, Swisscom, that gives an expensive but good service, then they think if I want to transport traffic from customer 1 to customer 2, I give usually a better service than ISP2. So for my customer, for customer 1, I will prefer to carry the traffic internally. So both exists and can be applied, as we have seen, by changing the rules of BGP. The BGP configuration differences that we've seen between those two examples are essentially on how routes are originated. So that is an important part of how you run BGP. What we have seen so far is how BGP propagates route information, but of course you need to start the process somewhere. So some routers must put into BGP which routes they know of, and this is not learned by BGP, it's learned by other mechanisms. Of course, you can always do that manually or by network management. So for example, in the lab, in the software we will use in the lab, which is called FRR, we will use the network commands to tell these BGP routers which are the prefixes it has to advertise. But this, of course, this is only for small networks. In large networks, there are essentially two methods: redistribution, which is either redistribute the connected, so it tells this router to automatically advertise all the prefixes that it knows of because it is directly connected to it, because its configuration as a router, BGP or not, is saying that there is a prefix on each of these links here. Of course, this will redistribute all the routes in this domain if all routers in this domain run BGP. That was, for example, the second example we saw last week, was applying this rule, redistribute connected. Another rule which is more frequently used is redistribute from IGP. IGP, remember, in the context of BGP means the interior routing protocol, OSPF, for example. So it says OSPF is used to distribute all the routes that I know of. OSPF can use external routes, or routes learned from BGP. We will talk about that in a minute. Of course, we should not consider those routes. So the idea is, with OSPF, we learn all the internal prefixes, and then the simplest is to redistribute all of them, if we care about redistributing all internal prefixes. Okay, so this is typically what was done in the first examples, where we saw two routers that were advertising all the networks that they've learned. So one way they can do that, they learned about it by OSPF. Of course, those are two extreme cases. In practice, very often, network operators redistribute not all routes they learned from OSPF, not even all internal routes, because some of their internal routes are typically not made to be known publicly, and very often they are even using private IP addresses. Voilà. So we have seen the very basic way BGP works. Now we need to address and understand one very important aspect of BGP operation, which is aggregation. We have seen that the principle of IP addresses is that it lends its well to aggregation. If we have a large number of addresses that are all can be aggregated by a single prefix, then it's better to do it, because it will reduce the size of the routing table. The routing tables, we will see in the worst case, if you are a transit ISP, it's close to 1 million for IPv4, 10 times less for IPv6. So it's still a large number, and we get much a smaller number with IPv6 because we aggregate a lot more. So aggregation is desirable in order to be a good citizen of the internet and make sure that the internet doesn't blow up through the sheer size of the routing table. But there are a number of side effects of aggregation that we will discuss. So first, let's examine here a scenario, and let me ask the following quiz. So here I'm assuming I have AS3 that is connected to two ASs that send him an advertisement for this prefix, 2001 Baba BB and 2001 Baba BibF, right, /48. AS3 asks the question, am I able to aggregate those into one single prefix? If I can, then that would reduce the number of announcements and the number of prefixes. What do you think? So I close the poll in a few seconds. And the majority says A, which is the correct answer. The two prefixes are contiguous. This is the necessary condition. You can aggregate prefixes that are only contiguous. Here they are, if the way they differ only by the last hex digit here, an E and an F, and I wrote here the binary representations. We see that they differ only by the last digit, which is a 0 or a 1. So if you ignore this last digit, which you do by saying /47 instead of 48, then you have a prefix that covers both. I can call it 2001 Baba BB. I could call it 2001 Baba BibF. It doesn't matter, because if I do the /47, I forget about the difference between E and F. So yes, it is possible to aggregate, and AS3 in principle should aggregate, and therefore should send to AS4 this common prefix here. However, there is still a catch here. What is the path? Because for those two sub-prefixes, the paths were different. The rules of BGP are that we can aggregate, and we give the information through this syntax here, the curly braces, indicate that the path is 3, 1, or 2. So this means an or. So we will be able to aggregate. AS4 will not know exactly whether the path for the subprefix is 1, 3, or 2, 3, but it will know it is one of the two. This is typically what is done in the internet. Okay, let's assume this is what AS3 did. So it has passed this information here, the aggregate prefix. But let's also assume that AS2 has a direct link to AS4 that AS3 might not even know. Why do they have that? Well, they have good relationship, or perhaps AS2 and AS4 are in the same country or serve customer bases that have a lot in common. So they want to peer with each other to have better relationship. So AS2 will pass this prefix here to AS4 here. Now AS4 has received those two prefixes, 2001 Baba BB /47, AS-path3, 1 or 2, and this longer prefix, 2001 Baba BibF /48, AS-path2 here. Assume one of the routers in AS4 receives those two, which will the decision process designate designate as best process. So here is a poll. I close the poll in a few seconds. The majority says B, which makes sense, but is not the correct answer. So that comes as a surprise. And here we have an important things to be aware of when we talk about aggregation in the context of BGP, is that for BGP, those are two different routes. They have different lengths, so that those are two different prefixes. So the routes that are to different destinations are not considered the same. Of course, you gave a different answer because you thought, and which is good, that one of the rules of BGP is that we can select only one route to a destination, which is correct. But here it's treated as two destinations. So the decision process here can decide not to accept some of them for whatever policy reason, but if it accepts them, then it is able to accept both, which means that there will be two overlapping routes. But if you think about it, that's very frequent. For example, when we have a default route to reduce the size of the routing table, for example, if an AS has all traffic that goes to Asia goes to the same neighbor, then it can aggregate all of this in the default route. So overlapping routes are very common. We always find them, and we must consider them different.
Jean-Yves, it's a mute from your side. Jean-Yves, you are muted.
Yes, thank you. So let me repeat. Assume that the decision process here, AS4, has accepted both routes. And in case you didn't hear me because I was muted, both routes are to different prefixes. And even if they overlap, they are treated differently, so we can accept both. Whereas, of course, if two routes would be for exactly the same prefix, that would not be accepted here. Now, a packet from AS4 goes to this destination prefix, 2001 BABA BIB-F /48. So the prefix that is advertised here. This packet is to be processed by AS4. Which way will AS4 send it? Will it send it via AS4, AS2, which is the shortest path, or via the longest path, AS4, AS3, AS2? Which one do you think it will take? I close the poll in a few seconds. Now the majority says B, which this time is the correct answer. The routers will do longest prefix match. So in AS4, there will be two routes for this destination, and the most specific will be used, which presumably will lead to the direct path here. This is what will happen.
Jean-Yves, you are muted again.
I think my microphone probably has a battery problem, so I changed microphone. Do you hear me now?
Yes.
Yes, okay. So here, assuming we have both, the packets will of course go the longest prefix MAC, will go through the more specific prefix. And we might wonder, why do we have both? Well, one of the key reasons is when we do BGP, we want to have as much redundancy as possible because many failures may occur. So, for examexample, here AS2 and AS4 have a direct link because presumably they have a lot of traffic and they want it to go directly instead of going via AS3, that is perhaps a provider and for whom they pay. But if this direct link fails, then what will happen? At AS4, the keep alive mechanism of BGP will detect the failure of the link here. The adjacency rib in, so AS4 has received this announcement, it will be declared invalid, and the best routes will be, and the best route, which is there's no alternative, the route will be deleted from the forwarding table, and then whenever a packet comes, it will match only the longest prefix, which will go the other way. So aggregated route here serves as a backup route, which is a very typical operation. Typically in the internet, with BGP, we express our preferences, but we keep the non-preferred paths as backups. Voila, so those are all the side effects of aggregation that are important. We'll come back to it in a different context in a few more slides. Before that, let's touch an important and tricky issue, which is how we go from the information that is in BGP into information that is usable by routers here. So far, we've seen how BGP routers learn about all prefixes. And when I asked questions about forwarding packets, I ignored the details of how the routers would learn it. There are two ways for doing it. One, which is natural and is very often done, but not always. Another one, which is not at all natural and was historically the most widespread one and is still done in a large number of operations. The first one consists in redistributing the routes learned by BGP into the IGP. What does it mean? Remember that redistribution is in the context of routing protocol, meaning when you take the information that has been acquired by some mechanism into another one. So here, BGP has learned things, put them into its forwarding information, into its, the decision process has selected a number of best routes. Then you can simply put this information into OSPF, for example. Of course, when you do that, you do only what is called redistribute internal. You don't want to give into OSPF the routes that have been learned internally. So you, in principle, do that only at the routers that have fresh information, because IBGP information is information that is second-hand, has been learned by some eBGP routers. So in order to avoid double redistribution, in principle, you do this. Then OSPF will propagate the routes to all routers in the domain. Now, so I said that's the method that makes sense because you learned about external routes at boundary routers, and then you inject that into the domain. That's the normal way of operation of OSPF. But it's not always done. The reason is that the size of the routing information that is learned in this way is very large. A router, a domain typically has a few hundreds of routers, sometimes thousands. So the size is nowhere comparable to the size of the routing tables of the internet. So most of the routes that are in a transit operators are external routes. So if you inject them into OSPF, that means most routes learned by OSPF are external, which works with OSPF, but requires a lot of memory and processing power. So that's a reason for some not to use it. Instead, what is done in parallel, but in fact overlapping with this, is called injection. Injection simply means that you put the information you have learned from BGP, for example,
into the routing table of this router. So the important thing is that this does not propagate. You do this only at this router. So you write directly from BGP into the routing table at this router. In all routers we've seen this is done systematically. So although this is historical, the normal thing to do would be this, but historically IGPs were not OSPF, they were not able to have large routing tables, therefore they could not do the redistribution, and therefore they did only injection. Let's see an example of redistribution. Here we focus on the central AS here, and I focus on the prefix 18.1. 18.1 is an external prefix for ASX, has been learned via eBGP by router 6, and router 6 will now redistribute into OSPF. Redistribution into OSPF simply means that R6 does as if it would be directly connected to some external prefix called 18.1, and it will typically give to this external prefix a very large distance. So R6 will say, I am connected to 18.1, and the cost to go there is very large. For example, in the lab, the software we use gives a cost of 20. Then, at this point, OSPF will simply propagate the 18.1 to all routers. So R1 will know through the topology database, there may be areas or there may be a single area, it doesn't matter. R1 will know how to go to this external prefix, and the same will be true by R2. Therefore, the thing is clean and simple intellectually, complex because now OSPF will have all the external routes, complex in terms of size of the data that OSPF will need to manipulate. So that is how redistribution works. As I mentioned, in the past and still today, many operators don't do redistribution, they do only injection. So how does injection work? Well, injection means that R6 injects the route 18.1/16 in its forwarding table, and R2 also, although R2 has learned it internally, but it knows about a route to this, so it will inject it into this forwarding table. Now, when you do this, what is the next hop? So this is a little poll. What kind of next hop would you choose here, in this case, at router R6? So I'm zooming on this router here. Will you choose R6 and R2, sorry? Will the next hop be 2222 or something else? I close the poll in a few seconds. Admittedly, this is a more tricky one. I close the poll. And the majority says B, which should be the correct answer. So you're perfectly right. The correct answer should be B, if everything would be clean. Otherwise, but unfortunately, this is not how things are. In fact, what is put into the routing table is not the next hop as it should be, but is the BGP next hop. So BGP routers, when they do injection, they write into the forwarding table the BGP next hop, which is on link at router 6, but is not on link at router 2. So in order to support this, we need to assume that the routers perform what is called recursive table lookup. So this is something we never discussed before and has been invented because of redistribution of BGP. Okay, do you hear me now? Yes, okay. So I have microphone problems today. Recursive table lookup means that we are allowed to write a next hop into the routing table, which is not on link, which of course doesn't make sense. The next hop is where you send the packet using the MAC layer. But in order to allow BGP to put into the routing table its BGP next hop, we allow this to happen. Of course, in practice, when you do this, the next hop that you find into the routing table is not useful. So you need to do a second table lookup to resolve the non-on-link next hop into one that hopefully is on-link. So this is exactly what is done in the context of BGP. Let's see an example here. Assume that this is the routing table at R1. So to a given destination, it has a next hop, which is 22263, which is this one. So this is because R1 runs BGP and has learned that for this destination, the next hop was this address, 22263. So it put it into its routing table. Of course, there is no interface field like there is when we look at routing table here. And hopefully, through OSPF or another IGP, we have learned a true next hop for this destination, 22263. Remember that for BGP, the next hop addresses are the addresses that are on boundary routers, and those boundary routers are treated as internal. So OSPF knows how to go into this to this destination address. For example, the next hop is 22233, this one here. So when a packet now is processed by router R1 and it finds a destination 10.1. something, it finds the next hop 22263, it will go again into the routing table. This is why it's called recursive table lookup. Of course, doing things recursively for a real-time process looks like a bad idea. Recursion is typically not compatible with real-time. So what is done, in fact, most of the time is that routers will pre-process the routing table by looking at all the next hop as a background task to look at all the next hop that are not on link and put a pointer directly through the routing table to go directly to the new line here. So in reality, you will not have a recursive operation, but intellectually, this is how things can be presented. So let's see how it would work here. So I'm assuming that the middle AS now is not doing redistribution, but only injection. So R6 puts into its routing table destination 18.1/16, next hop 222, which here is no problem. It's on link with R6. But R2, that has learned the destination via iBGP, will do the same. R2 will put into its routing table 18.1 destination and next hop 222. And because 222 is considered as an internal prefix in this middle AS, so the OSPF of this middle domain will find a route and will know that in order to go to 222, we go to R1 East here. So if a packet reaches R2, coming from this place here to this destination, the packet will be sent to R1 as expected here. Now the packet will reach R1, and then the next question is, what will happen at R1? Quiz. Time for a poll. I close the poll in a second. And the majority is fairly optimistic and thinks that the packet will be forwarded to R6 because R1 runs OSPF. However, through OSPF, R1 will learn nothing because the route is not injected into, is not redistributed into OSPF. So the sad truth is that in this example here, the correct answer is C. The packet will be dropped. R1 has no information about 18.1 because the only way it would have the possibility to know about it is if 18.1 had been redistributed into OSPF. But we assume here it's not done, we do only injection. So this causes a problem. So there is a problem. If we do only injection, we need to fix the problem. Believe it or not, a very common way to fix it is to run BGP also in R1. So if we do only injection, R1 will also run BGP. Remember that BGP can be run internally, so but with iBGP. So R1 via iBGP will learn the route from R6, other routes also from R2, then we'll inject it into its forwarding table with next hop 222. And then with recursive table lookup, that will solve the problem. So that's a first common mode of operation of BGP, which is that we run BGP in all routers, which is a bit weird if you think about it. If you go to an operator and you see that they run BGP in all routers, including in routers like R1 that do not peer with anybody externally, well, this is the reason here. In some sense, it is because we don't trust OSPF to be able to carry all the external routing information, whereas, of course, BGP can, because BGP must be able to carry the large sizes. So your implementation of BGP must be able to carry it. So people took the easy way and say, since BGP can carry it, let's use BGP, which is historically driven. When all of this emerged 20, 30 years ago, BGP was, of course, able to carry the internal traffic. Interior routing protocols, where OSPF was not as widespread as it is now, had a difficulty to run this. So this is why we find this method in practice, which is, as your answers to the quiz indicate, counterintuitive. But this is how the evolution led to this state of affair here. Of course, this has a cost. The cost is that we will need a huge iBGP mesh. We will need every BGP route, every router in the backbone to connect to every router in the backbone. So this is sometimes mitigated by other methods, like using default route if there is a structure in your network. And in the quiz, the online quiz, you will be able to discover this. I will say a few words about another alternative, which is used by many providers, that uses a concept that we will not discover in detail in this course, which is called MPLS. I'll just say a few words about this. MPLS is something that is run by large networks, also by industrial networks. So in the course on smart grid technology and the techniques used there, we'll talk about MPLS. In a few words, MPLS is something like VLAN tags. So remember that an IP packet is typically carried into an Ethernet packet or a similar type of name, PPP or SONET, SDH, etc. But those are all variants essentially of Ethernet, and it carries a MAC source destination address, which in that case would be just the MAC and source destination addresses of R1 and R2. And at the IP layer, we don't care about it. But we can have also a field called the VLAN tag, which is a logical identifier. Well, the VLAN tag can be used to separate virtual LANs. A variant of that, which is not called the VLAN tag, is called the MPLS label, can be used in a similar way if we use it for deciding what to do with the packet. So if a router, which is not just then an IP router, but also an MPLS capable router, receives a packet that has such a label, it will look up a label swapping table. Label swapping table means I will have a table that says for each label, where do I send this packet? The principle of label swapping table allows us to create paths that are below IP that go from one edge of the network to another one here. So in this context, for example, a BGP router that peers with the outside, like R6 and R2, would set up an MPLS path between the two here. But it's a tunnel if you want. So every packet that goes from R2 that should go to next hop 222 will go through this tunnel. In this way, R1 does not need to be aware of all the external prefixes. The only thing that R1 needs to do is how to send the packets to this next hop here. We could also use an IP tunnel. That means we could set up here the capability for R2 to send packets to R6. That would be very similar, but this is typically done with MPLS here. So in the routing table of R2, we would have, when a packet has destination address 18.1, it has next hop 222, and then the MPLS pre-processing at this node will say, oh, the next hop 222, which is this interface, the way I reach it is via this MPLS tunnel, and I put the label 23, for example. When the packet is received by R2, it's forwarded with an MPLS label 23. So this MPLS label is handled by R1, and R1 know now by static or dynamic configuration that whatever has incoming label 23 must go to R6 here. So this is what is done by a large number of operators. So they have internally set up tunnels between all inputs, between all external interfaces of their network, and when a packet comes, it goes directly via those tunnels here. That avoids the problem of putting into the IGP all the complexity of the external world, or the only complexity is the number of peering points. Now the reality is a bit more ugly, in particular in the labs that we have, the software that we have, which is the same as the dominant software found in the industry by Cisco and Juniper, always injects the routes into the forwarding table, even if these routes are redistributed into OSPF, for example, which means that in a case like this, if R6 redistributes into OSPF the route, R2, in principle, should not inject it into its routing table because it will receive it via OSPF. Nonetheless, through history, or in order to be sure that the route is not lost if things are ill-configured, these routers that we have, and I suspect most routers that run BGP in the world do that today, they inject all the routes, which leads to conflicts, because the same route may be learned via BGP or OSPF. So you need a way to re-establish the correct thing, and this is done by putting an administrative distance, which essentially is a priority field to a route that gives priority to eBGP over OSPF and over iBGP. This can even be used if you have multiple routing protocols to give priority to one or the other. Let's see an example here. Let's assume again we have this toy example and we do redistribution of BGP into OSPF. The routers such as R2 will therefore learn the route to 18.1 to two mechanisms. The first one is R6 has injected into OSPF, so R2 via the topology database, if it's a single area, will learn that there is 18.1 that's reachable here, and will calculate the next hop, which is R1. So there will be a next hop learned by OSPF, which is this one here. And the distance will be, for example, in that case, 2 plus 20, 22. But because R2 also runs BGP, it learns from iBGP this route here. And because R2 is pre-programmed to always put into the routing table the route learned from BGP, it will also put it here. So we will have a second routing table entry, which will be a recursive one. Next hop will be 222 here. And this one will not be used because the administrative distance of iBGP is superior to that of OSPF. Why this is done, I'm not sure, but this is exactly what is done. I'm not sure because the only value you could see to this is that if in case OSPF crashes, you don't run OSPF anymore, so you lose that information, you still have the other one. Except if OSPF crashes, you probably cannot run this network anymore, so you must have redundancy such that OSPF continues to work whatever happens. But in the lab, we will be exposed to that, so we will need to master this concept. Voila, that's it for this first part. So we do a short break and continue the lecture in 15 minutes or 14 minutes.